Hello and welcome to this lecture. We are in this multiple random variable module, and this is our 11th lecture. And as we are mentioning for some time in some previous lecture, that we will be give some brief introduction on copula, and this copula is useful when we are looking for the joint distribution of multiple random variables. So, today's lecture we will be considering a brief introduction on these copulas. This copula theory is relatively newer to this statistical theory, and just we will go through that brief introduction, and some special class we will just discuss, which is known as the Archimedean copula. Throughout this lecture we will try to communicate that how this theory or how these functions, these copulas are some functions, how these functions can be useful to derive the joint distribution of two random variable when their marginals are known. So you know that we have discussed earlier that even though the marginals are known, it may not be that easy to get their joint distribution. Only one meaningful conclusion that we have seen earlier is that if two random variables are jointly Gaussian, or their joint normal distribution they follow, then we can conclude that their marginals also will be normal distribution for each of the random variables involved. But the reverse is also not true. That is, when their marginals are normal, we cannot conclude that their joint will be joint normal distribution. So here we will be introducing some functions, some copula functions, and so using those functions we can derive that their joint distribution. This function follows some properties that has to be followed. So those properties we will be discussing, and after that we will be taking some of the specific example of these functions, and which can be useful, and what has recently found its application to the civil engineering problems. So our today's lecture is on this introduction to copula, and the outline that we have that we will follow is that first we will go through some basic introduction, and after that we will see its definition, its meaning, and its explanation, how what is this copula function, and we will see their properties, the certain properties that it should follow to first of all to be a valid copula. And there are some basic terminologies, as this is, as I told, that this is a newer area. So some of the basic terminologies we have to discuss, and while discussing these basic terminologies we will try to relate it to their one dimensional counterpart, because most of the theories we have discussed for the one dimensional cases, and so that as we have discussed it to the one dimensional cases, then now basically this introduction that we are talking about, like this similar to the earlier lectures, we will first discuss about in terms of the two dimensional cases, that is two random variables are involved, and even though later on we will just show that how these things can be extended to the even more than two random variables involved. So so that while discussing the basic terminologies, we will just try to relate that what is the counterpart on the single random variable, that is the properties of the single random variables, their PDF and CDFs. So that we will see, and after that there is one of the very important theorem which is known as the Sklar theorem, and basically this is the backbone of this full theory, from where I can use this function to obtain their joint distribution of the random variable involved. And that is generally done through some of the measure of dependence, and the dependence is generally the scale free measure of dependence. So we will discuss also on the issues of this measure of dependence, how we can measure the dependence from the population as well as from the sample estimate, that is from the sample of this data. And then we will discuss specifically about some the Archimedean copulas. There are different classes of copulas, for example the elliptical copula, placket copula, but here so far the many application has been found in these different problems of the civil engineering is through the Archimedean copula. So we will specifically see that what does this Archimedean copula means, and some examples of this Archimedean copulas also we will see towards the end of this lecture. Well, So, this to start with this word copula, this might be, even the word might be a little bit newer, that when we are this copula word is basically obtained from the Latin word which is known as copulare, copulare. So, this meaning of this word, this is basically a verb, and this meaning of this verb is that to join together. So, here as you know that we are just joining two marginal distribution of two random variables to obtain their joint probability density function or joint CDF. So, basically we are taking two marginals and we are joining them to obtain their joint distribution. So, that is the name has been taken from that Latin word, and this is the background of this word copula. In many cases, if we see of this statistical modeling, then we see that it is essential to obtain the joint PDF between multiple random variable, even though sometimes the marginal distributions of each of the random variable are known, their joint distribution may not be easy to obtain from these marginal distributions. So, this we have discussed earlier also, that we know that what is the marginal distribution, but for until and unless there are very specific cases, we cannot conclude that what should be their joint behavior. Say for example, if we just say that one distribution is say your one distribution is say that gamma distribution, and other one is the normal distribution, then what should be their joint? So, so far I think, if I am not wrong, then without the help of this copula, that kind of joint distribution cannot be obtained. So, that while getting their joint distribution, also we have to follow some of the measure of their dependence, and one of the scale free measure of dependence, that we will just discuss about what is the scale free means. That dependence between the random variable, that is one of the important parameter that we have to consider before we can go through that copula. Basically, so far as now I'll take some time to discuss on this dependence. Basically, the whatever the measure of dependence in this in the statistical theory is there, that can be broadly divided into two groups. One is that whether the dependence, whether the measure of the dependence is can change if I change arbitrarily the original data to some arbitrary scale factor. So, for example, that we are talking about the dependence between x and y. Now, for one of these random variable, either x or y, if I just make some changes to some scale changes, say that I make y, I replace y as y square. So, now the question is whether their dependence will change, that the measure of the dependence that we are considering, that whether that will change or that will not change. Depending on these two situation, this measure of dependence can be classified into two groups. So, one group is that it is irrespective of whatever the changes that we have made, the scale changes that we have made, and other group may change if we do this type of changes. So, the scale free measure of dependence means what we are talking, if we are going for that type of changes, that type of scale change, then this type of measure of dependence will not change. So, two such measure of dependence that we will discuss in this lecture is, one is that Spearman's rho, and other one is that Kendall's tau, that will come after some time. Before that, we will see the definition of this copula. So, the definition of copula, it says that this copula is a function that joins or couples multiple distribution function to their one dimensional marginal distribution functions. So, one dimensional marginal distributions for each of these random variable involved is available. So, this has to be joined, this has to be coupled together to obtain their joint distribution, and this is done through a function, and that function is indeed so that correspondence is one function, and that function is nothing but what we are talking about is that copula. So, and the second is the copula are the distribution functions whose one dimensional margins, or the margins means the marginal distributions, are uniform. So, now so this one dimensional marginal densities are uniform means when we are taking some random variable, and if we know their CDF, and if so from the CDF, if we go for the reduced variate, you know that CDF changes from has a range from 0 to 1. So, now once we know what is their cumulative distribution function, and if that cumulative distribution function properly represents that data, then if we convert that original data set to their cumulative distribution function, then that will convert it to the range between 0 and 1, and that will become one uniform distribution, and that thing can be joined together to get their to obtain that copula, that function which is known as copula. So, that is why the copulas are the distribution function whose one dimensional margins are uniform. Now, if we see it more intuitively, say here the example has been taken for the two random variables only, as I was just telling that suppose that there are two random variables x and y, and as I was telling their cumulative distribution function, that the for x the cumulative distribution function is fx of x, and this cumulative distribution function of y is gyy. Now, this fx x, so this cumulative function can take the values from 0 to 1. Similarly, that y also can take the value of this 0 to 1. Now, when we are talking about their joint distribution, so any point on this unit square, that is from 0 0 1 0, this is 0 1, and this is 1 1. So, in this unit square, any point basically represents a pair between the x and y. So, a feasible pair of this x and y. Now, suppose that this h x y represented through this lowercase of this letter x y. So, if this is their joint distribution and joint cumulative distribution, then following the properties of this cumulative distribution, this will also take the values between 0 and 1. So, the same combination of this x and y will correspond to one point on this unit square over the plane constituted by their cumulative density function, cumulative distribution function fx x and gyy. So, this is that point that we are talking about. Again, the same point will, the same pair, that x and y, the same pair will correspond to another point over this line from 0 to 1, which is their joint distribution, that is h x and y. So, so these 2 points, one is on this unit square and other one is on this line between 0 to 1, basically representing the same pair of this x and y. Now, these 2 points are basically these 2 pair basically they corresponds to each other through a function. So, this correspondence, the function that make the correspondence between these 2 function is what is known as the copula function. So, that is why that each pair x y leads to a point in the unit square 0 1 by 0 1, as we have shown that on this on the plane made by this fxx and gyy here that we have mentioned. So, this point, so each pair leads to that point, it leads to a particular point on this unit square, and this ordered pair in turn also corresponds to a number h x y in that 0 1 real line. So, so this is through their joint distribution. Now, both these points as correspondence. So, this correspondence between these 2 points is indeed a function, and this function is nothing but which is known as copula. Now, if we go to this mathematical definition of this copula, then this first of all we will discuss about this these two dimensional cases as we have started. So, this mathematical definitions also here we are discussing in terms of these two dimensional cases first. So, so this two dimensional copula, which is also shortly written as this 2 copula, is a function C prime with the following properties. So, this copula should follow some property, and those there are 3 properties. The first one is this domain of this C prime. So, domain means here you know that when we are talking about a single random variable, that time we have referred to the range of this random variable or the support of the random variable. Here, as it is the minimum is the 2 dimensional cases, and it can go up to means any dimensional cases. So, for that function we are defining is as a, for its entire range we are just talking about is domain. So, on what domain, that we have to specify some domain over which that function should be defined. So, the domain of that function C prime is S1 by S2, S1 cross S2, where this S1 and S2 are the subset of I, this boldface I containing that 0 1, that is I is the line between 0 1. This is basically what is meant through this mathematical notation is that. So, this domain of the C for a 2 copula is the subset of the unit square, which is made by this 0 1 in one direction and other direction also it is 0 1. So, this I is generally a this boldface I will be, because we will be using this notation again. So, this boldface I is generally written and with some power, and that power is basically indicating its what is its dimension. So, here if you see, that is if we write that this boldface letter I, what is referred to is that is one line up to 0 to 1. So, this range we are referring to this one. So, now if that boldfaced I, we just put that square, that is in the 2 dimensional case, then what we are referring to is that in a 2 dimensional space from 0 to 1 and from again other direction 0 to 1. So, we are referring to a square area over this 2 dimensional case. Now, if we just put that this boldface I as cube, then you can see that this what is referred is that is one 3 dimensional space where each axis, so 0 to 1, 0 to here 1 and 0 to here 1. So, you can just see that this will be a cube like this. So, this cube is that I3 that we are referring to. So, these are the notations what we mean by these symbols. So, here when we are talking about this domain of this C is that this is a subset of this I containing that 0 1 containing that 0 1 in this case as is I, it is that 1 to 0 to 1. So, this is the domain of this function and means that function means that copula. Now, the C prime is that function is grounded and 2 increasing. So, this grounded and 2 increasing, when we are referring to, basically we are giving some these 2 properties that it should follow, and it is having some correspondence to the 1 dimensional cases also, that we will take both these properties separately to discuss about this, what does this this terminologies basically means, that what is this grounded and what is this 2 increasing, that we will see in a minute. And the third property that it should follow is that for every u in S1 and v in S2, now you can see that there are 2 values that we are referring to for the 2 dimensional cases. One is in the direction of this S1 which is also between that 0 and 1, and other one is in the direction of the S2, which is also between 0 and 1. So this C prime U1 is equals to U. That means when the other variable reaches to its maximum point, that is its 1, then the value of this function should be equal to the value of the other attribute. Similarly, when U reaches to the maximum value, that means it is 1, then the value of this function should be the value of the other attribute, that is V. So these are the properties. So this is the maximum. Now you can see that this, the last one what we are talking about, the maximum limit that we have just defined, that is if one of the attribute is reaches to the maximum, what happens to this function. Now if one of the function is the minimum one, then what is the value of that function? That is basically is shown in this word, that is grounded. And another property is the 2 increasing. So we will take this grounded a bit later. First of all, we will see that what does it mean that 2 increasing. So so this is the first that basic terminologies that we are taking. In the first one is this 2 increasing function. So what does this 2 increasing function means? So a 2-dimensional analog of the non-decreasing function is a 1 dimension. So this is the first point that we are talking about, is that is that how it is corresponds to what is its corresponding counterpart in the 1-dimensional cases. Now if you see here that for a 1-dimensional function, we have seen for its CDF that it starts and it's reach up to 1. It can be asymptotic or it may not be asymptotic. It can touch it over its entire support. It should, from the left extreme of the support, it should start from 0, and to the right extreme of the support it should reach to 1. So that is the range of this CDF. But the other thing that we have already seen that this function is a non-decreasing function. So non-decreasing means it should be the, if this is your say x1 and this is your say x2, and we can say that the x2 is greater than x1, then these values, that is say f of x1 and this is x2, f x2, then what we see that if x2 is greater than equals is greater than x1, then that f of x2 is greater than f of x1. So that means it is an increasing function, it is an strictly increasing function, but we should include one equality sign here also, just to state that this is a non-decreasing function. So it doesn't mean that whether between these 2 points it will increase or not, it can even remain flat for this region and it can again go, but it will never come down. So this will be either greater than, or it should be, at least it should be equal between these two values of this function at point x2 and at point x1. So so this is what we have seen in this 1-dimensional cases. Now if I want to extend the same property to the 2-dimensional cases, then what is known as is known as the 2 increasing function. So what does this? So this is the correspondence between the 1-dimensional cases what we have seen earlier, and the corresponding thing, the same corresponding property in the 2-dimensional cases is known as that property that it is 2 increasing function. Now a 2-place real function is 2 increasing if h volume of the rectangle B is greater than equal to 0. So again here we have got 2 more new terminologies. One is that h volume of the rectangle B. So first of all we have to know the which rectangle we are talking about, and if we know what is the rectangle, what does this h volume means. So that we will see, and this is for these rectangles B, and this should be valid for all rectangles B whose vertices lies in the domain of H. So we have to know that, so domain we have seen that it should be the domain of the C, that we know that it is within this 0 1 and 0 1 this bound, and we have to know that in this domain if there we can identify one rectangle and what is that edge volume means, and that edge volume should be greater than equal to 0 to satisfy the condition that the function is 2 increasing. Now let us discuss about this, what is this edge volume means. Now let us see this this area first, that is the one rectangle that is whose vertices are the x1 y1, this is x2 y1, this is x1 y2, and this is x2 y2, and if we say that this this rectangle is in the domain between this 0 and 1, that is the domain of that function, and if from this rectangle also you can say that, or if we just specifically mention that x2 is greater than x1 and y2 is greater than y1, then this is what this rectangle what we can see in this form. Now so this is the plane by the two random variables. Suppose that this side it is x and this side it is y. Now the same rectangle is again represented here on that plane. So this side is your x and this side is your y, and this is that rectangle that you can see here. Now to see that what is the edge volume, we mean that for that one we have to first see that how that joint CDF between that xy looks like. So this is, as you know, that this should start from 0 and it will go on and reach to a maximum value reach to a maximum value of 1. So this is your that h xy axis, and this should be your here 0, and this one this line it should be written as 1, which is missing in this figure, but you can easily make out that this is the starting point is your 0 and this is going up to a maximum value of this 1. So this surface that you can see, suppose that is that is the joint CDF function in a two-dimensional case. So two-dimensional function, that means this is a surface. Now that edge volume when we are talking about, so it is just like that one surface is given there and you are cutting that surface through this through the lines of that rectangle which is shown on the base. Base means on this surface considered by x and y. So now if you cut this this surface is just like a slicing the cake along these lines. So what you will get is a volume like this. Now if you get the volume like this, then what you are getting, so you will get 4 ordinate at these 4 vertices of the rectangle shown on this ground, means ground means here on this surface. Now that value that we are talking about is your this h x2 y2 is nothing but is the what is the ordinate at the point x2 y2, that means at this point what is the value of that joint CDF function which is shown by a black vertical line here. So now that h volume of this rectangle is this one, this height minus this height minus this one plus this this height at x1 y1. So if we just go back to this original rectangle, then the value of the function at this point minus value of the function at this point minus value of the function at this point plus value of the function at this point. So this is giving you the h volume of that function, h volume over the rectangle B, which for which the vertices are as shown in this figure, that is x1 y1, x2 y1, x1 y2 and x2 y2. Now if just if it is not that difficult to even remember that this is what we are taking is that first we are starting from this extreme right top corner minus other two diagonals plus this one. But if you say that why this one, it is also, it can also be easily referred in terms of the CDF. Basically what does it mean, that what is this ordinate here at this x2 y2 means, if we see that this is a joint CDF, that is cumulative distribution function of this one, then what this ordinate means is nothing but what is the total volume covered by the PDF probability density function up to this point. Now instead of considering this CDF over this plane, if you just consider what is the PDF, means the probability density function over this one, so what you will get is that so that it can be, you can see that as a surface again over this zone, over this area, means depending on the support of these two random variable x and y, and what is the total volume that is covered up to this point, which is represented by this ordinate when we are talking this when we are taking this surface as its CDF. Now if I just represent that same rectangle here, and if we want to see that if for this rectangle, if we want to know what is the volume over this rectangle when I am considering considering their joint PDF over this zone, then what will happen for this one, for this point, to get that what is the volume above this rectangle, then what I have to do, that I have to first take what is the total volume. Suppose that this is the left extreme of the random variable that we are talking about, then or I can even just say that why to take that, it can be say that minus in infinity. Then what I am talking, that I am first taking the full area up to this point, what is the total volume up to this point, this should be, now to get only this rectangular area, then I have to deduct this area first. Let me use other color. So this total area minus this area minus this area, that means now you see that in this process this area has been deducted twice. So this area should now be added, which is nothing but the total volume up to this point. So that is why the total volume under the PDF, remember total volume under the PDF probability density function up to this point minus total volume under the PDF up to this point. So this area I have first deducted, then this area is again deducted, then I have to add this area because this area has been deducted twice while deducting this point and this point. And this is why this, when we are talking about this H volume, that means that time we are taking that this area minus so this ordinate is nothing but the total volume under the PDF, that just now what we discussed. So this one minus this ordinate plus this one. So this gives you the H volume over this rectangle. Now if I want to say that this function is always increasing in both the direction, in the direction when this x1 when what I say that x2 is greater than x1 and y2 is greater than y1, then this volume should be, the volume below that PDF should be greater than equal to 0. So that is why, so this volume should be greater than equal to 0, which is represented as VHB, and that is why the requirement here is that VHB should be greater than equal to 0. So this is what actually is the meaning of this 2 increasing function. But remember one thing, that only this condition, that is VHB, that is H volume of this B, if it is 2 increasing, that does not guarantee that every direction, that is x and y, both the direction, that function also will be non-decreasing. That is not assured. So, but we know that the marginals, the marginal distribution also is a non-decreasing function. To assure that one, what is the other condition is there, that also should be satisfied. Then that other condition is that it should be grounded. So, what does that grounded function means? So, that is here, that is shown here, that is this grounded function here means that a 2 increasing function does not imply that h is non-decreasing in each argument. However, if it is 2 increasing and grounded, the h is non-decreasing in each argument also. Okay. So, these are the, after we discuss this grounded, these are the conclusion. But before that, what is this grounded function means? So, you see here this this line that we are talking about, and this line is h, the value of that function h is 0 at this line segment. So, what does this line segment means? That is, when one of the argument is 0, either u or v, means which is the reduced variate for the x and y. If either one of these u and v are 0, then the value of the function is 0, and that is what is known as the grounded function. That is, at both these lines segment, the function is starting from the ground. So, now if I go back to that one of this, this property, what we discuss here, that if one of the values are reaching to its maximum value, then value of the function is equals to the value of the other attributes. So, that is c prime u1 is equals to u and c prime 1 v is equals to v. Now, the by the word grounded, what we mean is that if one of the argument is 0, then the value of that function equals to will be equals to 0. That is, c prime 0 1 is equals to 0 and c prime 0 v is equals to 0. So, irrespective of what is the value of the other one, that means here I should say that c prime u 0 equals to 0 and c prime 0 v equals to equals to 0. So, this is what is meant by this grounded function, which is represented through this diagram here. Over this line segment, the value of this function should be equals to 0. Now, as we were just telling that it's simply, if we just say that a function is 2 increasing, that does not imply that in both the argument means in both the random, in the direction of the random variable, is does not guarantee that whether they will also be non-decreasing or not. But if we say both the properties, that it is 2 increasing as well as it is grounded, then we can say that it is non-decreasing at each argument also. So, which is obvious because their marginals are also one CDF, which is non-decreasing, so that their joint function, that is the property of the Copula function, should be 2 increasing as well as it should be grounded. So, a copula, and here it is a two-dimensional case, is a function with the domain is I square here. Now, I square, just a few minutes before I have discussed, so it is a two-dimensional plane bounded by 0 1 and 0 1, that is vertices are 0 0, 0 1, 1 0 and 1 1. So, it should have the following properties. One is that this is grounded, as I told, it is c u 0 equals to 0 and c v 0 equals to 0, and other one is that when it is reaching, one of the argument is reaching to its maximum value, that is c u 1 equals to u and c 1 v equals to v. For every u 1 u2 v1 v2 in I, such that u1 is less than equals to u2 and v1 is less than equals to v2, then the copula function at u2 v2 minus the value at u2 v1 minus the value at u1 v2 plus the value at u1 v1 should be greater than equal to 0, which is nothing but it is ensuring that the copula function is 2 increasing, and this full statement is nothing but the H volume. So, one example of this copula which is that we use it also earlier, that is that independent, if the two random variables are independent, then we know that their joint distribution is nothing but the product of their individual marginal distribution. So, say that if here that that particular copula function will be is equals to your CUV equals to U multiplied by V. So, when we can say that their joint distribution is their product of their individual marginal distribution, then we know that this is one their joint distribution is the product of their individual marginal distribution. Now, this is also one copula, and which is known as the independent copula. So, this function is known as the independent copula, where this u range of this u and v both are varying from 0 to 1. So, and if we represent this one, how this copula function looks like, it will look like this. So, it will start, you see that both the functions are it is grounded, both the functions are starting from this line segment. Over this line segment the value is 0, which you can also cross check from here, that just if we put that one value is equals to 0, then the value of the function becomes 0. And then if one of the function reaches to its maximum value, that is if u equals to 1 and v is any value, then the value of the function is v, and vice versa. So, here that is reflected through this line, which is a straight line, 45-degree straight line through this plane. This is that direction of this copula function. This is one of these random variables. So, this line is a 45-degree line over this plane. Similarly, this line is also a 45-degree line over this plane, which is the other random variable versus that function of this copula. So, at 0.55 and this 0.5, you can see that if one is reaching 1 and other one is 0.5, this value of the function is 0.5. Just for one example, and this is true for entire this straight line, and which is also can be cross checked from here. So, if we just put one value equals to 1, the value of the function is equal to that value of the other attribute. So, this is also satisfied. So, this is a copula function which is satisfying its required property, and that function looks like this surface that you can see here. And also the another way of representing the copula is the contour diagram, and the contour diagram is shown like this, where you can see that these different contours are shown with this different color bar. Here the color bar is not mentioned here, but you see that this blue one is 0 and this red one is 1. So, in this way it is gradually increasing. Obviously, the copula, these values of this contour should be mentioned here to properly represent what is its what is the height above the ground of this surface. Now, there are one more property related to the bound of this each copula that we should discuss now. So, this is known as that Frechet-Houepding bound, FH bound, abbreviated form. That this FH bound, it says that the any copula function should be bounded by two functions, and those functions are that the minimum, the lower bound is that maximum of u plus v minus 1 comma 0. So, in these two, u plus v minus 1 or 0, whichever is maximum. So, this is the lower bound of that function, and minimum of u v, this is the value of the upper bound. So this is generally represented by this W u v, and this maximum one is represented by this the upper limit. Upper limit is the minimum of u and v. The upper limit is represented by this m, u and v. So why this is W and why this is M, there is no these are just the notation, but you can just for the sake that this is the lower bound, that is the lower side, the way the word W is written, that the lower side is just bounded, and the way the M is written, it is the upper side is bounded. This is just for the notational sake only. So this is that your lower bound and this is your upper bound of the copula function. So that this lower bound is the maximum of this u plus v minus 1 and 0, and the upper bound is the minimum of u and v. So how does this bounds looks like, that we will see now. So first we will take this lower bound here. So these are the two surfaces that we have drawn, is that this is the lower bound and this is the upper bound, and these are their corresponding contour diagram. So now you see that whenever we are talking about this lower bound, on this floor of this 0 1 and 0 1, on this floor, if I just draw the diagonal here, then up to that diagonal the surface is on the ground, and from there, from this diagonal of this base, we are just connecting to this upper side, other side corner. So this is a straight surface. So this is the bound, this surface and this one is the lower bound. This we can also cross check, that is when we are just talking about, say that u equals to 0.5 and v equals to 0.5, that time the value of the surface should be at 0. Right. So if we just see one or two such values, then u equals to 0.5, v equals to 0.5, which is equals to 1 minus 1 is 0. So maximum of 0 and 0, so which is 0. So in this way, if we take whatever the combination that we take, which is coming to this this side of this diagonal of any combination of this u and v, then we will see that this value will become 0. So which indicates that this surface is basically on the ground up to this diagonal, and after that it is going and touching these values, where this side you can see that this is also means when one is reaching to this maximum one, the value itself is that value of the other attribute. So that suppose that just put one of this value as 1, so the v equals to 1, so this 1 is cancelled, so the maximum of u comma 0, and you know that u is always greater than equal to 0, so the maximum value is u. So so that is what is reflected here, that when one attribute is 1, the value of the surface is at the value of the other attribute. So this is the lower bound, and similarly the upper bound also we can see this is the minimum of u and v. So just if we take any values, say that one is say that 0.5 and other one is 0, so there is a minimum of these two, that means at this point the value will be 1, and if I take that 0.5 and 0.5 both, so it is the minimum of both the values, so it will go, and this height here at this point 0.5 also will be 0, which will be more clear through this contour diagram. You can take any combination of these two, and their point will be the minimum of the combination. So on this line the minimum value is always 0.1. So that is why whatever irrespective of the value of this axis, this value is always 0.1. Similarly, in this way we can just say this is one straight line. This is just like a half of a pyramid, that kind of surface. You can see that this is one surface of the pyramid and this is another surface of the pyramid. So that is the way this upper bound is defined. So what is important here for the copula function is that, so now you can see that this is what we are talking about is the lower bound, and this is what we are talking about the upper bound. So any surface which is representing a copula function should lie in between these two surfaces. So basically I can place this surface over this, and you can imagine that there will be a empty space between these two surface, and all the copula function should lie in that space, and that is what this upper bound and the lower bound of the copula function pictorially represents. Now, the Sklar theorem, which is the most important theorem in this theory of this copula, through which we can connect or we can join, we can couple their marginal distribution to have their joint distribution. Let that hxy is a joint distribution function with marginal distribution fxx and gyy. Then there exists a copula C such that for all xy in I square, you know that what is this I square we defined earlier. So, for all xy combination, that hxy, this is joint distribution, is equal to that C of, that is a function of that fxx and gy. If f and g are continuous, then C is unique, otherwise C is uniquely determined on the range of f and range of y. So, this is consisting that surface over this range, over this area, this should be uniquely determined. On the, so this is the Sklar theorem. In the other in the conversely also we can state that if C is a copula and fx and gy are the CDFs of their random variable, obviously the x and y, then their joint distribution is equals to their copula function of fx and gy of y. So, if we have that fx and gy, then we can get that through this copula function we can obtain their joint distribution, which is hxy represented to this xy. So, this is the joint CDF of the random variable xy with the margins, means the marginal distribution fxx and gy of y. Now, as I was telling that we will be taking the measure of dependence through which basically this copula function should be defined, because there is a parameter in the copula function that generally preserves that scale free measure of dependence. So, that the two scale free measure of dependence we will discuss here now. The first one is the Spearman's correlation coefficient, or the Spearman's rho, rho s. This should be rho, this the rho s, which is the through this copula, if it is expressed that it is 12 of this double integration of u v d c. So, with respect to c, that copula function, if we integrate this function minus 3, this is the form of the Spearman's rho, which can be derived from this copula. Similarly, the Kendall's tau, there is a Kendall's correlation coefficient, or Kendall's tau, is equals to the 4 times the integration of this copula function with respect to dc minus 1. So, this is representing that Kendall's tau, and this tau and rho s follow the inequality that this 3 times tau minus 2 times rho s, this is generally bounded by from this minus 1 to plus 1. So, even though these functions that we have discussed in terms of this through this copula function, these two measure of scale free dependence, but for the real time time series or the data that we are having, if we want to know what is the scale free dependence, then we have to go for some sample estimate, and from the sample we will first estimate what is the Kendall's tau, and from that Kendall's tau we will first find out what is the parameter of the copula function that we are taking, and after that we can obtain what is the complete definition of the copula for the data in hand. So, in the next class what we will do, we will just we will discuss first how to estimate this measure of dependence from the samples, and we will discuss a particular class of copula which is known as the Archimedean copula, and that and there we will show that how we can estimate from the sample and get the complete form of this copula function, which can be used to, and ultimately we will be deriving their complete form of this joint PDF. So we will discuss these things in the next class. Thank you.